Hello, friends. Last time we were together, we learned the fundamentals of calculating pH, but not of a particular substance. And that's what we're going to do here today. We're going to learn how to calculate the pH of a strong acid or a strong base. Last time we were together, we saw that pH is equal to the negative log of our hydronium ion concentration, H3O plus. That's the important ion. And as I look at my three example problems I have here, I have hydrochloric acid, nitric acid, hydroiodic acid. All are strong acids. None of them appear to have hydronium associated with them. But that's because we're forgetting that when you put a strong acid into water, it ionizes 100%. That means all of the hydrochloric acid that I start with here is actually going to end up turning into hydronium. So I end up with Cl minus and I end up with H3O plus. It's the H3O plus that we care about, but I want to show you how we should think about this. Initially, before putting this into water, we have 0.015 molar HCl. If I then put it into the water, all of it will ionize. So at the end of the process, I'm going to have none left. On the other side, I start with 0 of my products, but gain 0.015 molar of each. Now you may say, how did you make 2 times 0.015 molar when you only started with 0.015 molar on the left? Again, this is a big concept in chemistry. We're really just looking at ratios. They're in a 1-to-1-to-1 ratio. Okay, so equivalent amounts of Cl minus and H3O plus are made, and we shouldn't confuse that with meaning that we have, essentially 0.015 molar HCl is dividing into 2 and doubling or anything like that. They're just in a 1-to-1 ratio. So at the end of the process, I have 0.015 molar Cl minus, and I have 0.015 molar H3O plus. Now here's the thing. I really only care about this number because that's my H3O plus. So if I want to find the pH of this particular solution, it's going to be the negative log of 0.015 molar. In most cases, that's all you really have to do. So let me get my calculator out. Negative log 0.015, and I get a pH of 1.82. 1.8 is fine. Okay? Now, there's a lesson here. For strong acids, as soon as you recognize that it's a strong acid, you know that all of it turns into H3O plus. So I don't really have to go through the process of writing out the entire equation. And as soon as I know that, I can find the pH. So in this case with nitric acid, if I take the negative log of my initial concentration, 2.5 times 10 to the minus 4 molar H3O plus, that should give me my pH. Negative log 2.5 times 10 to the minus 4. I get 3.60. Much lower pH because of much lower starting concentration. The only thing that can get tricky with strong acids is if you start with an exceptionally dilute acid. Okay, look at that concentration there, 10 to the minus 9 molar. What I would kind of set as the boundary is anything that is less than 1 times 10 to the minus 7. And we'll talk about why in a minute. Look at what happens when you have really dilute solutions of acid like this. We can assume that it all turns into H3O plus. And I can find the pH, or at least I think I can find the pH by taking the negative log. So if I say negative log of 4 times 10 to the minus 9, I get a curious answer. Negative log 4 times 10 to the minus 9. I get 8.4. That can't be right. Let's talk about why. 8.4 is a basic pH. This is an acid. An acid should not have a pH that is basic. So what's going on here? Well, it turns out one of the things that we forget is that in pure water by itself, you have a reaction that takes place in very small quantities. Water reacts with itself and produces OH minus and H3O plus. One of the things that happens in pure water is these are quite well-known concentrations. Most of the time they don't matter, but they're both 1 times 10 to the minus 7 molar. Well, when you have a very dilute solution of acid like we do here, the amount of H3O plus that you get from pure water, 1 times 10 to the minus 7, is actually greater than the amount that you get from the strong acid, hydroiodic acid, 4 times 10 to the minus 9. Long story short, anytime this exponent is smaller than 10 to the minus 7, here's what we should consider doing. We should say the pH is just equal to the negative log of the H3O plus produced in pure water, 1 times 10 to the minus 7, or 7. Okay? Long story short, when you have a very dilute acid, it's almost like having pure water. Let's stop right there. We'll come back. We'll talk about strong bases in our next video.